And we can start. So I know I've been slightly late on the links and telling people what we're reading for this section, so sorry about that. But yeah, after having a look myself at the material, it was more appropriate to do one section. I think we were doing one section per week before the chapter 3, so I think we'll be going back to that regime, especially since for me as the I'm having to do more work starting this week, so yeah, I'll have less time to do this as well. So anyway, so welcome to chapter 4. So we just left chapter 3 on the functional derivative, and now we're entering chapter 4 on Hilbert spaces. And I think it's safe to say that Hilbert spaces is like the sort of the last really big chapter, big ideas in this book, and the other ones then are sort of building upon that chapter. So we're pretty much almost at the end of this book. And if we look at the sections for chapter 4, we're doing this week we're doing the basic introduction to inner product spaces, and then we'll have all these later sections about orthogonality, best approximations, and Fourier series and stuff. Those all build on the basic ideas of inner products and how we generalize these ideas we have from essentially Euclidean geometry. And then again, there's a conclusion on the applications to that on quantum mechanics. So at least one of the ways you can formulate quantum mechanics is exactly in terms of Hilbert spaces. And it's relevant, for example, in quantum computing and so on. So today's menu is that, okay, we have Banach spaces, they're nice, but by default they lack several very nice operations. For example, we'd like to be able to take the angle between two vectors, because if you take the ideas of vectors as some kind of straight lines, then we'd like to be able to say, okay, I have two vectors, what is the angle between these two? Similarly, if we can take the angle, we can also say, oh, if I have a 90-degree angle between two vectors, then that means vectors are orthogonal. And from orthogonal vectors, we get orthogonal bases. And of course, these are very useful when we deal with finite dimensional vector spaces. And another very useful application is if try to solve some kind of shorter distance or best approximation problem. For example, if you have some kind of surface, some kind of manifold in your space, you have a point on side it to find, okay, what's the closest point, the closest point on my manifold to my point. Then if at least if you're in finite dimensions, you can just say, okay, it's the orthogonal projection, because you know that the closest point has to be such that the tangent plane to that point is orthogonal to the normal in the direction of your other point. I'm not being very clear, but essentially for that we need to have this notion of angle in geometry, and to do this we'll need to generalize the notion of inner product or the dot product to general vector spaces. And actually in doing so, really what we'll be able to do is to do geometry in function spaces. Like really what if we have just the norm, we have some kind of topology, but if you have an additional inner product, we have a notion of angles. So for example, we can also say, okay, with talking about the cosine similarity, we can do really Euclidean geometry on our vectors, infinite dimensional vector spaces. So without any other introduction, let's start with what actually is an inner product. So here we have the axiom of an inner product on a vector space. And note that here we say that a vector space over some field K, but really they mean either the reals or the complex. And it's a bit unfortunate because it means that everything we'll see in this section is not completely general, because it does not quite extend as easily to vector space over arbitrary fields. So it's more of an esoteric point, but it's especially in the exercise, it feels a bit, I have to think, okay, I have to do the real case and then the complex case, and it feels somewhat inelegant or incomplete. So anyway, an inner product is just a function that takes two vectors and returns a scalar, and it has to satisfy that apply to xx to the same vector twice, it has to be greater than 0, and if it is equal to 0, then that means that my vector x is the 0 vector in my vector space. it also has to be linear with respect to the first argument. So you have the additivity to the first argument and take the scalar out. And we have this fourth axiom, which really is only important in the complex case, is that if we swap the order of our operands, then we obtain the complex conjugate of the or the other inner product. And this combined with the first two laws means that our inner product is somewhat also linear with respect to the other argument, but each time we have to take the complex conjugate. So, for instance, if you take the scalar, so if at x alpha y be equal to alpha complex conjugate xy. So it's easy to forget if you're only dealing with the real vector spaces, but in complex vector spaces, which are technically more general, you can get easier tripped up by that. So these are the axioms, and interestingly or very nicely, in any inner product space, X is also a norm space. So we can define a norm just as simply the square root of our the square root of the inner product X with X. Note that within the axiom we had this thing that kind of looked like the positiveness of our norm. So indeed it checks out. But note importantly that not all norm space are inner product space. So it's a very really special case, and you can think of it as if your space is an inner product space, you have some additional constraints, and those really show in the theorems that are true for inner product spaces but aren't in general. One example of that is the somewhat famous Cauchy-Schwarz inequality that says, okay, if you have an inner product space, then the inner product or the absolute value of the inner product of the x and y is smaller than the product of their norms. And moreover, we have the equality when x and y are linearly dependent, as in, for example, y is equal to some scalar lambda times x. But yeah, not the Cauchy-Schwarz is very useful, especially when you're measuring like sequence spaces and you're trying to find at least bounds on some sequence. But it's in general, it's maybe not the most useful in this section. And we can have other example of inner product spaces. So for example, simply the R to the n or C to the n with the Euclidean norm is trivially inner product space. We also have, and that's the part where it can be a bit tricky. That, okay, we take the space of square summable sequences. For example, this space of sequences is R such that the series of x absolute value of x square converges. Those are the square summable sequences. That is a Hilbert space, not yet a Hilbert space, but an inner product space. And similarly for functions, we have this space of, okay, I have maybe continuous functions such that the integral of their absolute value squared is finite, and that is also an inner product space. Although note that if you try to, so the end goal is to have something that not just an inner product but also complete, so also a Banach space. And specifically for this case, you have to actually redefine what you mean by taking the integral here. So it's not the Riemann integral like most people know.
Do you not get an inner product space if you don't take the square part?
Sorry? So,
if you replace the 2 with a 1, do you not get an inner product space anymore?
No, you don't, and we will actually see a nice way to prove that, actually. So, excellent question. But yeah, so far we had only inner product space, but they're not necessarily Banach space. So we still have to add the requirement that Cauchy sequences are convergent sequences, and so when you have that, so both an inner product space that is Banach, so complete, that's the Hilbert space. And there's actually a very funny story about that. Is that so? Of course, Hilbert spaces are named after David Hilbert, famous German mathematician from basically 100 years ago. And he was really one of the first people to actually work seriously with these infinite dimensional vector spaces and define axioms for them. But the use of the word Hilbert space to denote these kinds of vector spaces was not started by him. So he was very confused. There's a funny story about him going to a seminar and hearing people talking about Hilbert spaces and being very confused by actually what they meant. So the legend says that he raised his hand and said, "Okay, but what actually is a Hilbert space? I'm very confused." So it's very funny to imagine Hilbert asking what Hilbert spaces are. Although I couldn't find like a concrete citation for whether this is true or not, but I think it's probably true. But yeah, one of the nice theorems that holds in Hilbert space but doesn't hold in general is the parallelogram law. It says basically if we have an inner product space with the induced norm here, then for any vectors x and y, we have that the sum of the square, so the squared length of x plus y and x minus y is equal to 2 times the square of the norm of x plus 2 times the square of the norm of y. And the reason this is called the parallelogram law is because this is really a theorem from Euclidean geometry, where if you have a parallelogram, then take the square of these two diagonals, it's equal to the squares of all their sides. So really, this is sort of puts a nail on the idea that because we have a Hilbert space, all of these intuitions we have from Euclidean geometry, even 2D Euclidean geometry, still works. And this is one of the reasons why Hilbert spaces are really useful and are a more comfortable place to be than just regular old Banach spaces.
I think this is also like a double implication, this identity. Like if you can prove a norm has this
Yes.
property,
Yeah,
it should
exactly.
also...
That's a good point. They mention it in the book as well. That if you have a norm space that satisfies the parallelogram law, then you can recover the an inner product space. So any norm space that has the parallelogram law is a Hilbert space or is an inner product space. The way we can get that is using something called a polarization identity. It basically says that at least in the real or complex case, we can always recover the inner product from the norm. So in the real case, we just take the squared norm of x plus y minus the squared norm of x minus y and divide it by 4. And the way we get that is really using the parallelogram law. In the complex case, it's a little more complicated because we have this imaginary part that gets added. And really this is useful because for any norm space, you could use this formula to try and define what the inner product should be. And okay, you did something that looks like an inner product, but if you're not in a proper inner product space, then you'll find that it won't work properly. And the nice part about this is that we can actually use this to show that, for example, L2, so the squared sequence is the only LP space that is Hilbert. And for example, we can also use it to show that the space of continuous functions defined on the draw 0 to 1 with the absolute norm is not Hilbert, and this is exercise 4.1. And so this is pretty useful because you can use it to show that some space is not in fact a Hilbert space. So this goes back to your question, Gorkenglass, about okay, can we show that some other spaces is or is not Hilbert? This would be the easy way to do it, actually. So some further theorems, of course, since we were talking about Euclidean geometry, Pythagoras theorem still works. So if we have two orthogonal vectors, then the squared norm of their sum, the sum of the squares of their norms. Another nice property, which is somewhat not too surprising, but actually quite tricky to prove, I found, is that the inner product is a continuous map. And finally, this one is pretty nice because you can also define any product on M cross N matrices by simply taking the trace of A transpose B. And this induces the book, they call it the Hilbert-Schmidt norm, but it's better known as the Frobenius norm, exercise 4.1. So this is pretty nice because it means you can take the a space of matrices and actually consider it as a inner product space. And of course, because it's a finite dimensional space, it's automatically Hilbert.
Is there a notion of trace for linear operators?
I think there is, but I think it might not quite be work as you might think. So I would say yes, but there are some. Of course, as soon as you step into the infinite case, something's break. So anyway, I wanted to spend a bit more time on this last big exercise and really this last big theorem of this section is that given some inner product space, so X with the so it's X inner product, it is incomplete, so it's not Banach. We can actually always construct or enlarge X into a space X bar such that X bar is complete, and we can identify X with some subspace of X bar. And the proof is pretty interesting, at least the sketch of the proof. I will be skipping some tedious details for the sake of communication, but I thought the proof was pretty interesting, and I didn't quite understand it all at first, so I think we'll be covering it right now. So the main trick actually here is to start with taking the set of Cauchy sequences on X, because we have a space such that not every Cauchy space is convergent, so we have in a sense some hole, right? Because if we say, okay, I have a Cauchy sequence that does not converge, that means I have a sequence that gets closer and closer to itself, but somehow I cannot find exactly where it lands. So it sort of points at some kind of hole in my space, some kind of missing point. So sort of natural idea, okay, let's take the set of all the Cauchy sequences on X, and we'll be defining an equivalence relation on these Cauchy sequences. We'll say that two Cauchy sequences are xn and yn are equivalent if in the limit, I forgot to add the next part, but basically the limit goes to 0. So essentially we have two Cauchy sequences and they get closer and closer to each other as well. And this is in fact an equivalence relation. And if we take the quotient set of our set of Cauchy sequences by this equivalence relation, so when I say the quotient set, we said we're taking the set of equivalence classes of C under this equivalence relation. So an element of X bar is a set of all these X and Y's that are equivalent to each other. And we'll be using so this notation bracket X to denote the equivalence class of X some sequence. So we know that this is a set of sequences that are equivalent. So this sort of makes the proving stuff about these elements a bit more tedious, because we can't just say, oh, it's just this sequence. No, we have to take into account that it's a set of sequences that are equivalent, so proves to have to use that. And it's pretty easy actually to define vector space operations on X bar. So we clearly said the addition of these two equivalence class is simply the equivalence class of xn plus yn, where x and y here are some elements or some representative element from our equivalence class, and the trick is to prove that okay, it doesn't matter which one we take. And similarly, we can scale by some scalar by simply okay, it's the equivalence class of our representative elements scaled by alpha. Furthermore, we can also show that we have an inner product space by defining our inner product on X bar as the limit again of our so the limit of the inner products in X of our representative elements. And note that we are allowed to take the limit here because this is sort of the important part. We are allowed to take the limit here because it's somewhat easy to show that the sequence x and yn is Cauchy, because x and y are Cauchy. So this sequence is a Cauchy sequence in R or C, and because C and or R are complete, of course then there are convergent. really this proof hinges on the fact that our scalar field is complete itself. I think it's why we have to sort of restrict ourselves to R or C for the sake of simplicity. But note that here there are some sort of non-obvious assumptions or non-obvious steps made in thinking this limit. And we can also trivially embed our original space X by mapping some element X simply the constant sequence of X. So we basically as into we take an element X in X and we map it to iota X being simply the sequence X, 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 X. Of course, this is a Cauchy sequence, so it does work. And we can take the equivalence class. So really, this is about to say, okay, we can map our elements to the set of all the sequences that converges to that element. And furthermore, it's pretty easy to show that the inner product on these mapped elements is still the same as the product of these elements regardless in the original space. Now the last part is sort of the most difficult, is to show that okay, we have this X bar that is an inner product space with all these nice stuff, but is it complete? And this is where it gets a bit mind expanding. Is that it says okay, well, let's take a sequence xk x, and what is this object here? It's a Cauchy sequence of Cauchy sequence, or at least a Cauchy sequence of equivalence class of Cauchy sequence. So we have a sort of double Cauchy sequence going on, and I mean, this is the part that confused me at first. And basically, we show a new sequence Y. So because we're in the Cauchy sequence space, or at least equivalence class of Cauchy sequence space, our limit has to be a Cauchy sequence again. So we'll be constructing a new Cauchy sequence YK, such that our Cauchy sequence of Cauchy sequences converges to Y. Go on.
I have a guess at what the collected one is, and I think everyone could benefit from like 20 seconds to think about it.
Yeah, maybe I'll leave 20 seconds for people to think about it. Any other questions while we're at it? Okay, then I think I'll be moving on to the rest. To define our limit, or at least candidate limit, basically use the fact that we have a sequence of Cauchy sequences. So since each xk here is a Cauchy sequence, for each k then we can find some nk, such that for all mn above nk, we have the distance between x and xm, both for our the kth element of our sequence is smaller than 1 over k. And we actually take that, we say that define our sequence y as yk being, so we're taking the kth sequence and we're taking its nkth element. And this will be our candidate for the limit. Note that here the 1 over k is somewhat for simplicity's sake, but because we're dealing with Cauchy sequences and equivalence classes of Cauchy sequences, really it's somewhat arbitrary which one we take, as long as no. Fortunately, the rest of the proof is sort of the meat, but it's also A, not friendly to showing on slides, and B, not exactly insightful, but the rest of the proof goes somewhat as follow. So take some epsilon greater than 0, do some epsilon twiddling to find that indeed our candidate limit is a Cauchy sequence, so it is in C, so it makes sense to speak of its equivalence class, and then do some more epsilon twiddling to find that indeed our sequence of Cauchy sequences thus converges to our candidate limit y, but candidate limit in terms of equivalence classes. I'm sorry for maybe getting your hopes up for a full proof, because this might be a letdown, but honestly the proof itself is pretty gruesome. So if you're curious, I invite you to like read the one from the book, and maybe work it on paper, because it's confusing. But really the main takeaway from this part is that we can take any inner product space and complete it by replacing its element with equivalence classes of Cauchy sequences. So it sort of takes some time to wrap your head on, okay, what exactly does this mean? But really, we can also think of real numbers completing rationals in much the same way. Although there's some technicality, we don't actually need to do that, but it's useful to think of real numbers as really equivalence classes of equivalence class of Cauchy sequences in R. So really, when we're taking the step from the rational to the reals, the object we're manipulating are completely different, right? Because the reals are really some kind of sets of sequences of rationals. So I hope you can sort of feel the weirdness behind that. And this exercise or this theorem was about doing this for inner product spaces, but this construction can be broadly adapted to complete any incomplete metric spaces. This was how we learned the construction of real numbers in real analysis at school. Wow.
The basic idea of the proof is just that you take the sequence of sequences and arrange it in a two-dimensional grid, and then the sequence construct is just going down the diagonal, right?
Yeah, somewhat, because you're not quite going through the diagonal, because you're taking these right. If you look at the definition of Y, we're sort of asking, okay, I want my I'm taking the n to the kth element of the kth sequence, and n to the nk might not quite be to get the 1 over k. So it's not quite a diagonalization here. But
because every sequence in the sequence of sequences might converge more slowly than the last, so you sort of have to pre-process them, throw out a bunch of elements until each of them converges at the same speed?
Yeah, I think that's pretty much that. But yeah, essentially you're taking your sequences, you're sort of zipping them far enough that you get close enough, get where you want. Yeah, but this will, as was about to conclude, do note that, so I said, okay, we can apply this sort of construction to generalize any incomplete metric space. And one sort of the nice example, I think there was an exercise at the beginning of the book about that, is that you can take the the rational numbers and define other kinds of norms on them. So, for example, a p-adic norm. And we can also define, okay, what is the completion of the rationals with respect to the p-adic norm, and we get a completely different set from the real numbers. So it's interesting because there's an entire field of p-adic numbers built on that, where you have a field that extends the rationals but is completely different from the reals. So this goes back to sort of my slightly disappointment about this section, because we're still only dealing with real or complex vector spaces, and it's not fully general. And when you do the exercise, it feels a bit, I wish this didn't need to be either one of the two. But I guess for the sake of brevity, at least, this was the right choice. But yeah, this was all of the slides I had for today, so let's move on to the discussion.
Can you tell us what inner product spaces or Hilbert spaces are for? Like, what is the strongest theorem that holds exactly for them or something?
Oof, I don't quite have that in my head, unfortunately, but really it's much nicer to be in a Hilbert space than in a regular Banach space, because you have all these different properties. For one of the nice ones is that the dual space is isomorphic to your original space, which does not hold in general Banach spaces, and this is quite useful. Sorry, go on.
I think you can even prove something stronger where like every Hilbert space is isomorphic to some particular type of, I think it's like L2, little L2 working on a possibly uncountable set.
Yeah. Is it similar to the way that like the ring of integers is sort of the mother ring that all finite rings sort of come back to, or?
Yeah, I think in some sense, like essentially you have like the uncountable case, the countable case, of course the finite case too, but aside from that, they should be pretty much isomorphic. Like if you have different Hilbert spaces.
Yeah. But to give you more examples of useful properties that are easy to do in Hilbert spaces, say you want to find, you have some finite amount of vectors, or you have some subspace of a Banach of a Hilbert space, and you want to find, okay, I have an arbitrary vector in my space. What is the closest vector from my subspace to that vector? And in Hilbert space, this is very easy to do. You just do the orthogonal projection, and it works. But if you're in just a normal Banach space, like orthogonal projection doesn't even mean anything. So it's all these cases of, okay, I want to have an orthogonal basis of my space, and really the Hilbert space, the kind of space that you can find a good, nice orthogonal basis. And it's very useful, for example, when you want to do spectral analysis, and indeed one of the sections is about Fourier analysis, and this is just that. In a sense, when you take the Fourier decomposition of a function, you're taking the decomposition of your function in an orthogonal basis, because the Fourier basis is an orthogonal basis of our Hilbert space of functions. Any other questions or comments, right?
Yeah, you also mentioned the duality thing being isomorphic to itself, and you represent it like a scalar product. So essentially, it's like the L2 case where you can see duality as just hyperplanes in space. So even that helps a lot, like in applications.
Yeah, and I think really like if you want to do PDEs, or if you want to do any kind of numerical application of functional analysis, it's much more comfortable to do it in a Hilbert space than in a general Banach space, because at least you have some grasp on the object you're manipulating, which you don't
Yeah,
necessarily
also
have.
like quantum mechanics too has that bracket notation. So which basically means the duality being isomorphic to itself.
Did anyone try to do some exercises, or at least had some time to do? Because I didn't have all the time, to be honest, so I have not managed to finish all of them, I don't think. If people have some exercise, or maybe if you're looking right now that maybe you'd like to discuss. All right, then. If no one has any other questions or exercises, apparently not. Okay, let's see. Maybe there's people in voice. Yeah, Edu, this is another reading group about functional analysis. You may have heard us talking about math. This is more math. Yes. Cool. Maybe you should check out the channel then. Anyway, so since I think we're pretty much at the end, since I don't have any other questions, so as I suggested back in the beginning, we probably should go back to the one section a week, especially since I think each section here has sort of enough content to really digest properly in a week. So the next section is about orthogonality. So we're digging really into what it means to have orthogonal vectors in these infinite dimensional code spaces, presumably how to define orthogonal bases, and then it moves on to other applications. Presumably it will be next week. I'll be posting the when is good tomorrow morning. But yeah, other than that, I think we can wrap it up. Tough crowd today.
All right, thank you very much.
Yeah,
Sorry, go ahead.
also, one question, because there was like the complex case versus the real case, but like, aren't there other type of like constructions, like instead of starting from the real field or complex field, maybe something else?
Yeah, that's what I was sort of lamenting, is that I think it's usually, at least usually in first courses, you only consider the real or complex case. But I definitely felt unsatisfied doing this. That but I want to consider just an arbitrary field, not just the real complex. But I think like some of the proofs we've done here, they hinge on the fact that, okay, to show that our space is complete, we actually have to use the fact that our original field is complete. So because it really goes, okay, we assume that we need to use the fact that R and C are complete to prove that our spaces built on them are complete. So
Yeah, I was thinking maybe the p-adics could work.
yeah, but although I wonder how would the polarization identity work for the p-adics, for example, if it's there a nice easy way to define what the polarization identity looks like.
No, I was mostly thinking because like there in the complex case there's the conjugate operation to add to.
Yeah.
And I was wondering like if there was like some motivation, because usually like it's okay to give it for like if you do the calculations you see it's right, but
Yeah,
I don't know if
I
there's
think
like
the reason you need the complex conjugation is that you want the positive definiteness when you take the product of some vector times itself. And so in the complex case, if you think even just finite dimensions, so take like n dimension vector of complex coordinates, and you take its inner product, you'd like the inner product between its transpose and itself to be the sum of the squares, or at least the sum of the squares of the modules of its elements. So to get that's why to get the if you want, so if you have a complex number and you want the square of its module, you take the product with its complex conjugate. So I think that's why we need to take the conjugate for the complex case. Yeah, I'd be very curious to see. I think I have some other books that might go into more abstract detail about construction. I'll have a look. And to answer Edu, yes, this group does meet somewhat every week. It depends. Sometimes.
Is there set material that you go over? Like, if it's a sort of reading group, or is it just you discuss the topic
yes.
in
This
general?
is a reading group. If you look at in the alignment general, there's a thread called functional analysis reading group. You can look at there. And
okay, I see. Thank you.
there's a pin post about so we're reading a book called A Friendly Approach to Functional Analysis.
Cool. Right. Thank you.
Yeah, sure. Okay then. I think I had all I wanted to say. So unless there's Any last minute questions? I think we can wrap it up there. Thank you all for coming.
Thank you.